Right, so for the next few weeks we've been talking about a new topic which is called differentiation, and this topic is part of the bigger topic called calculus. Now, calculus is a whole branch of mathematics that was invented years ago. And calculus was invented by Isaac Newton, but at exactly the same time, it was also invented by a guy called Gottfried Leibniz. So two different inventors at two different times, but it's a really important branch of mathematics that's going to come up this year and next year. And probably if you ever go to study engineering, maths or physics, you'll definitely be doing some calculus later on in life as well. So what calculus is it's a study of change. More specifically, it's a study that looks at infinitesimal. So it looks at infinitely small intervals and how small changes in x will have changes in y. We can use it to work out gradients, we can use it to work out areas of things, but yeah, very important branch of mathematics. So basically, calculus will let us find the gradient of any function. More importantly, differentiation will let us find the gradient of any function. So we'll start off talking about gradients again, so a quick recap of when we looked at gradients in coordinate geometry. So remember, gradient is a rate of change of y with respect to x. So it's how y changes when you change x. If you make a little change in x, what that does to our y values. And we looked at calculating it for a straight line. So if I take a couple points on this line, we'll have x2, y2, and x1, y1. And we looked at the difference in the y values divided by the difference in the x values and came up with the gradient m equals y2 minus y1 over x2 minus x1. So nice and easy for a straight line. Just find 2 points and find the difference in the y values divided by the x values to work out the gradient. So we now want to be able to calculate the gradient for any function, not just lines. We need curves, we need exponentials, we need trig graphs as well. So we need something that works for all of those. And this is going to be where calculus comes in. Before we get into the calculus, though, we need to talk about functions and come up with a new notation for describing functions. So we looked at this a little bit back when we did transformations. But so a function basically is any operation that you can put x values into and get out y values. So our notation for it is we could say f of x equals x squared. And this would be basically saying our function is x squared. So the function is square the x values. Now, if I wanted to calculate a specific value, a specific y value for this function, we could use the notation f of 2, which would basically mean put in x equals 2 for this function. So we'd get 2 squared, which gives us 4. So in other words, for an x value of 2 on this function, we get a y value of 4. So f of 2 is 4. So we can use functions to notate things like this. What we're going to use for gradients then, there's going to be two different things. One that's in terms of y, but we're going to kind of do away with calling gradients m. Gradients now, we're going to get functions for gradients, which we're going to call f of x or dy dx, which is basically the same as the gradient. This is going to be a new notation. Gradient function, which we'll talk about a bit later. So we're going to start off with x squared as the function that we're going to try and find the gradient of. So our function f of x, we're going to look at x squared. So I'll plot this quickly and we'll go through how we're going to do this. And there we go. So it's not a straight line. but we can still find the gradient of this using similar methods. Now, what Newton and Leibniz came up with was we're going to take two values on this curve, and we're going to say these values are infinitely close together. I know in my sketch they're not, but it's because I can't draw two infinitely close points. It wouldn't look right. So we're going to just draw them anywhere. We're going to call this point x, and the y value for this is going to be f of x. And then we're going to choose a point that's infinitely close to it. And how we're going to kind of notate this is we're going to say h is an infinitely small number. And we're going to say our x value for this point is going to be x plus an infinitely small distance. So if that's x, this is going to be x plus h. So we're going to say our x value for this is x plus h, which is just x plus a tiny difference on the x-axis. Okay, so what's our y value going to be? Well, if we put in x is x plus h, we're going to get the function of x plus h as our y value. So there's our x, there's our y, there's our x, there's our y. Now, if you zoom out on any graph enough, and you've got 2 points right next to each other, they will always resemble a straight line. And the straight line will approximately have the same gradient as the curve at the point you're looking at. So we're going to use our gradient equation, but with these points to try and work out what the gradient of this line is, and that will tell us the gradient of f of x in general. So we're going to say our gradient, we're going to use the new notation. So f of x is going to be gradient function. Our gradient is going to be the difference in y's, y2 minus y1, so y2 minus y1. Divided by x2 minus x1. Cool, right, so we're going to do this specifically for x squared. So x squared, here's our function. So we're going to have f of x plus h is going to be x plus h all squared, and f of x is just going to be our original function, x squared. So we get our gradient function. It's going to be x plus h all squared minus our original function, x squared, all divided by x plus h minus x. Cool, so theoretically if we expand everything and then simplify, we should be able to work out what the gradient is for any point on x squared. Notice we've done this really generally. We said for any point x, there's a point infinitely close to it, x plus h, and using that we can find a general gradient for any point on this curve. And because obviously the gradient is different at every point on this curve, we're not going to get just an answer like the gradient is 2. We're going to get an equation that tells us the gradient, which we call the gradient function. So let's give that a go. Let's try and find out the gradient function for x squared. So let's write this up again. F of x plus h. X plus h squared minus x squared over x plus h minus x, and that's going to be our gradient function. So if we expand the top, we get x squared plus 2hx minus plus h squared minus x squared, all divided by x plus h minus x. And then we can try and go through this simplified thing. So all I've done, expanded the top, subtracted x squared, and wrote it out again. So on the top, we're going to get our x squareds are going to cancel, leaving us with this. And we've got on the bottom, we've got x plus h minus x. So the x's here are also going to cancel, leaving us with the gradient function. Here's 2hx plus h squared over h. And we can divide through the top and the bottom by h. So h divided by h, they're going to cancel. And h squared divided by h, we're going to get just h. So our gradient function, 4x squared, 2x plus h. Now, over here we said h is an infinitely small number. Because it's infinitely small, we can approximate and say that h is roughly equal to 0. So over here, my equation, h is going to go to 0, leaving us with the gradient. So that x squared, the gradient of x squared is going to be 2x, because the h is going to be 0. So in other words, if you differentiate x squared, if you want to find the gradient of x squared, you get 2x. And that's our proof for it. So this proof has a name. This is called proof from first principles. So it's the first principles of differentiation. And we can formally write out our proof like this. So we say f dash x equals f of x plus h minus f of x divided by x plus, or divided by h even. So generally we get this equation. So the gradient function is f of x plus h, so the function when x has got this tiny little distance in it, minus the original function divided by the tiny little distance we had in the first place. And that will give you the gradient of anything. So we're going to try another example. We'll try and find the gradient of x cubed. So we're going to use our gradient equation. F dash of x is f of x plus h minus f of x divided by h. So if f of x in this case is x cubed, f of x plus h is going to be x plus h cubed. So in other words, quick sketch. We've taken an x value and a value infinitely close to it, found the y values. This works for any function. We're now going to find the gradient between those 2 points. So up here, this equation is going to become f dash of x is f of x plus h, which we just said was x plus h cubed, minus f of x, so minus x cubed, divided by h. And we can again simplify this like we did before. So I'm going to expand the top using binomial expansion quickly. So we get x cubed plus 3 x squared h plus 3 h squared x plus h cubed minus x cubed all divided by h. So expanded the top, subtract x divided by h. Now we can simplify. So again, we're going to get x cubed cancels with x cubed. We're going to now divide each term by h. So we got our gradient function 3x squared h plus 3h squared x plus h squared over h. H is going to cancel a lot of these terms out, so that should be a cubed. So we get f dash of x is 3x squared plus 3hx plus h squared. Now, as h tends to 0, it's going to mean that this term and this term both go to 0. Because if h is 0, 3 times 0 is 0, and h squared is also 0. So our gradient function of x cubed is going to be 3x squared, as we can see here. And you can do this with any function you like. So we'll do one more example, and we'll go through f of x is 1 over x. So find the gradient of f of x equals 1 over x. So if f of x 1 over x, f of x plus h, I'm going to put that into our function and get 1 over x plus h. So our gradient function is going to be f of x plus h minus f of x, which is 1 over x, all divided by h. So again, we're going to try and simplify this and find out what the gradient actually is. So if we subtract two fractions, remember we need to find a common denominator. So in this case, my common denominator is going to be x plus h. So we're going to get x plus h minus x plus h over x plus h, all divided by h. I know this is a triple layer fraction, but we'll sort it out in a second. So I'm going to subtract these two fractions now and write them as one fraction. So x minus h over x plus h all over h. Now, because I hate free layer fractions, I'm going to write this top fraction being divided by h to sort things out. So f dash of x is x minus h over x plus h divided by h. So it's no longer a free layer fraction, and I can actually work with this side without worrying about this. So x minus x is going to be just disappear. So we're going to get rid of our gradient function is minus h over x squared plus hx. And we want to divide this whole fraction by h. Now, if two ways you can think about it, you can either divide every bit here by h, or you can, the easiest way of thinking about this is just timesing it by 1 over h. So remember, if you're dividing fractions, so remember as a fraction this is actually h over 1, we can flip this fraction and just times them. So we're going to get f dash of x is minus h over h times x squared plus hx, and these h's here can just cancel, so we're going to end up with our differential function is minus 1 over x squared plus hx. So last step, as h is infinitely small, h is going to tend towards 0, so this, our gradient function for f of x, which is 1 over x, our gradient function is going to be minus 1 over x squared. Cool. Alright, so we've done 3 of these. Let's summarise everything we've done so far. So for f of x, and here we've got f dash of x. So if f of x is x squared, we found that the differential of that was 2x. If f of x was x cubed, we found that the differential of that was 3x squared. And for 1 over x, remember 1 over x, we could say is x to the power minus 1. When we differentiated that, we got minus x to the power minus 2. Because remember, minus x to minus 2 is 1 over minus 1 over x squared. So there is a pattern going on here. We did everything from first principles, but there's a quicker way to find these gradient functions. And the rule you get, some of you might have spotted it, if you times by the power and then subtract 1 from the power, we get 2 times x. We can imagine this is the power 1. Next one, if we times by the power, we get 3x, and then take 1 from the power, we get 3x squared. Even for this one, if we times by the power, we get minus 1x, take 1 from the power to the power minus 2, which is what we got here. So the rule is, if f of x equals x to the power n, where n is any number, the gradient function is going to be nx to the power n minus 1. And that's how differentiation works, and we call this the gradient function, because it is a function that gives us the gradient at any point. Cool, so that's the gradient function, gives us the function at any point. Right, so because we don't use this all the time, sometimes we just use y equals. We get the same thing over here. We can say y equals x to the n. And the way we show we differentiated something is we say dy by dx equals n x to the n minus 1. So it's a different way of writing things. These mean the same things. Y is x to the n, the function is x to the n. The differential of y with respect to x is nx to the n minus 1, or here the differential of the function is nx to the n minus 1. So both of these is how we describe the gradient function and how we show examiners that we've done some differentiation by doing this. So our summary for differentiation so far, that's how we differentiate things. Cool. Right, so in words, what we're doing is we're timesing by the power. And then we're subtracting 1 from the power. So for some examples of this, we're going to try some now. So, e.g., find the gradient function of 5x to the power 4. So if I want to say y equals 5x to the 4, we're going to say the gradient function dy by dx is times by the power, so 5 times 4 is 20. Then we get x, take 1 from the power, so we're going to get x cubed. So 4 times 5 is 20, and then x to the power 3. So that is our final answer for that. That's the gradient function. Alright, let's try another one. Oh, actually, if we wanted to find the gradient of this equation at a point, we could just put the point in there. So, e.g., find the gradient of 5x to the 4 when x equals 1. So all we're going to do to find dy dx, so it'll be the same thing again, 20x cubed, but we want to find out the point 1. So the way we do that is we put a line here, and then we put x equals 1, and now we're going to say 20x to the... what am I talking about? Let's do that again. So differentiate it, we get dy by dx equals 20x cubed. And to find it at the point 1, we're just going to put 1 in here as x, so dy by dx, you can do this by saying x equals 1, so we've shown them that we put in x as 1. That gives us 20 lots of 1 cubed, so the gradient is going to be 20. So for this graph, y equals 5x to the 4, the gradient is 20 at the point x equals 1. So let's try another full example like this. So alright, so find the gradient of this where x equals 1. If you want to pause it and have a go, do it, but I'll do it now. So dy by dx times by the power, so 3 times 7 is going to be 21. So minus 21, drop the power by 1, so x squared. Then here, 2 times 3 is going to be 6, x to the power 1. So you can write to the power 1 if you like, or you can just call it 6x. But it did say it wanted it when x equals 1. So dy by dx when x is 1 is minus 21 lots of 1 squared plus 6 lots of 1 to the power 1. And you want to show them that you put the point in. There's a method mark just for putting your value into your differential equation. So here we get minus 21 plus 6, which is going to be minus 15. So if you like, our gradient at this point is minus 15. And later on we're going to be finding tangents and normals to curves at random points using gradients that we find out by substituting x in. Cool. Alright, that's it for today. So that's differentiation. Differentiation from first principles was where's it gone? This stuff we looked at earlier. So this finds us the gradient of any curve and shows the proof for it. So we need to learn this as a proof. So going through the method of putting x plus h in. But try both those bits out in the video, and then be getting more of this next lecture.